Hello everyone, our lesson today is about photoelectric effect. In order to answer a question, how does this photocell works, we need to know what is photoelectric effect. First, let's discover the objectives of this lesson. At the end of this lesson, the student will be able to define the photoelectric effect, state Planck-Einstein's hypothesis, and interpret photoelectric effect by Planck-Einstein's hypothesis. Let's define the photoelectric effect. Photoelectric effect is the emission of electrons from a metal when illuminated with a convenient, suitable electromagnetic radiation. Here we have a metal, it contains infinite number of electrons. When a certain radiation hits the surface of this metal, it may extract some electrons from this metal. This phenomenon is called photoelectric effect. Here we have a little experiment about photoelectric effect. Okay, consider a negatively charged zinc plate illuminated with a monochromatic radiation of wavelength lambda. We have an electroscope. The zinc plate is negatively charged. Okay, so the plates of the electroscope repel each other because they have same sign charges, both are negative. Okay, now we will hit this zinc plate with infrared radiation. Okay, we observe that the plates of the electroscope remain in their initial position whatever the intensity and the duration of the infrared radiation, so there is no photoelectric effect in this case. Using a visible light, also the position of the plates remains the same. The visible light has a greater frequency than the infrared radiation. Okay, so it has greater energy. Now we will use ultraviolet radiation. Okay, suddenly the angle between the two plates decreases instantly, as we see in the figure, so we can deduce that the plates loses electrons, so photoelectric effect takes place. When ultraviolet light shines upon a zinc plate, it causes the plate to emit electrons. Now let's discover what is the condition for photoelectric effect. Okay, the previous experiment leads us to the following result. For a pure metal, the photoelectric effect takes place only if the frequency mu of the incident radiation is larger than a certain limiting frequency mu 0 characterizing this metal. Let's first define the threshold frequency and the threshold wavelength of a metal. Threshold frequency mu 0, okay, it is the minimum frequency of incident radiation necessary to release electrons from a given surface of a metal. Okay, in order to release electron from a metal, the frequency of the radiation must be larger than this limiting value. Okay, threshold wavelength, it is the maximum wavelength of incident radiation necessary to release electrons from a given surface of a metal. Okay, so any radiation must have a wavelength less than this threshold wavelength lambda 0 in order to have photoelectric effect. Okay, to extract electrons from the metal, the frequency or the wavelength of the radiation must be mu greater than mu 0 or lambda less than lambda 0. In the table below, the threshold frequency and wavelengths of some radiation. Okay, now let's talk about work function or extraction energy. By definition, the work function or extraction energy W0 of a certain metal is the minimum energy needed to extract an electron from the surface of this metal. Okay, the work function equal to hc over lambda 0 equal to h mu 0. W0 is expressed in joule because it is energy, and here we have new constant called Planck's constant h equals 6.6 times 10 to the power minus 34. Here we have an important note. Joule is considered a huge unit relative to the energy of the radiation, so we express the energy in this chapter in electron volt. Each 1 electron volt equal to 1.6 times 10 to the power minus 19 joules. Okay, here in the table work function of some pure metal. The need for particle theory of light. Okay, why do we need to talk about particle theory of light? According to wave theory, okay, as we saw in diffraction and interference, light considered as a wave. Okay, but now light must be considered as a particle. So according to wave theory, the energy of any radiation propagates continuously, okay, and progressively. So after a certain time, the energy must accumulate or gathered, okay, and the electron must finally be extracted. In this case, it contradicts with the experiment of part 2, because at the experiment we observed that there was an instantaneous emission of electrons, okay, and according to wave theory, the energy of radiation does not depend on the frequency. So whatever the value of the frequency of the incident radiation, the emission of electrons must take place. In this, it contradicts also with the existence of threshold frequency. Part 6, we will talk about Planck's and Einstein's theory of photoelectric effect. First, let's talk about Planck's postulate. The interaction between radiation and matter is quantized. Quantized means takes place with multiple specific discrete values of energy called quantum. The energy carried by each quantum is equal to E equal h times nu equal hc over lambda. The energy carried by the radiation quanta, which is the sum of quantum, is equal to E total equal n times h mu. Okay, so the radiation consists of n number of quantum, so the total energy will be n times h mu. Now, let's talk about Einstein's postulate. Okay, the electromagnetic radiation consists of photons. So the radiation consists of infinite number of photons. Each photon has an amount of energy called quantum. Okay, and the energy of this photon is h mu, as Planck's said. A photon is uncharged particle of zero mass and moves in vacuum with the speed of light c. The energy of electromagnetic radiation is quantized. Okay, its radiation has its own energy related to its own frequency. Upon collision, each photon can transfer its energy to a single electron. The energy carried by photon of frequency mu is E photon equal h mu, and the total energy of the radiation is related to the total number of photons, so it will be equal to n times E photon, where n is the number of photons in the radiation. Application 1. A red radiation has a wavelength lambda r equals 700 nanometer in vacuum. Calculate in joule and in electron volt the corresponding photon energy. Here you need to pause the video and to try to solve the application. Solution. First, you write the formula E equal h mu equal hc over lambda. Then we substitute the values of hc and lambda. Okay. Lambda we transform from nanometer to meter, we multiply 10 power minus 9. The answer will be 2.8 times 10 power minus 19 joule. Okay, in order to transform from joule to electron volt, we divide by 1.6 times 10 to the power minus 19. The answer will be 1.8 electron volt. Interpretation of the photoelectric effect. When a photon of frequency mu hits the surface of work function W0, three cases may be considered. First, if frequency of the radiation less than u0, so h mu less than h mu 0, so energy photon less than W0. Okay, in this case the photon is reflected from the metal without extracting any electron. So in this case, as we observed in the first figure, there will no photoelectric effect because the photon cannot extract the electrons from the surface of this metal. Second case, if the frequency of the radiation equal to the threshold frequency, so h nu equal h nu 0, so energy photon exactly equal to the value of the work function. In this case, the photon is absorbed and the electron is extracted from the metal, but with the zero kinetic energy. Okay, so we have photoelectric effect, but the electrons leave the metal at rest. Radiation is greater than the frequency, the threshold frequency, so the energy of the photon greater than W0, the extraction energy. In this case, the photon is absorbed and the electron is extracted from the metal with a kinetic energy. So when the electron is extracted with kinetic energy different from 0, the energy of the incident photon is equal to the sum of the work function W0 of the metal and the kinetic energy of the extracted electrons. So E photon equal W0 plus maximum kinetic energy of the electron equal to H mu 0 plus half mv maximum squared. Okay, this relation is called Einstein's relation of photoelectric effect. Conclusion: the photoelectric effect supports the corpuscular aspect of light, and each incident photon may only interact with one electron, okay, no matter the amount of energy it carries. Here we have another application. Also, you can pause the video and try to solve this application. Okay, the wavelength of the radiation is 300 nanometer. The work function of the metal is 3.4 electron volt. The question here, is there any electron emission? If yes, what is the kinetic energy of an ejected electron? And we have H and C are given. Okay, the solution: first you need to calculate the energy of the photon. Okay, you substitute the values and you will obtain that the value of the energy in joule is 6.6 times 10 power minus 19, and in electron volt 4.13 electron volt after you divide by 1.6 times 10 to the power minus 19. Okay, you compare this value to the work function, so you can conclude that energy is greater than W0, so we have photoelectric effect. Okay, the kinetic energy of the electron is the difference between E of the photon, energy of the photon, and W0. Application 3. In part 8, we will talk about graphical study of Einstein's relation. Okay, here we represent the kinetic energy of the extracted electron versus the frequency. Okay, the curve will be a straight line passing, not passing through the origin. It can be seen from the graph that the curve of kinetic energy as a function of frequency is represented by a straight line not passing through the origin. So its equation must have the same form as y equal ax plus b. So kinetic energy equal a mu plus b, where a is the slope. Okay, when we compare this equation obtained from the curve to the Einstein's relation, okay, Einstein's relation, E photon equal W0 plus kinetic energy maximum, so kinetic energy equal E photon minus W0 equal H mu minus W0. By comparison with the equation above obtained from the graph, we can conclude that or deduce that the slope of this straight line is equal to h. So the slope of this line is Planck's constant, and b is equal to minus W0. Also, the intersection between the curve and the x-axis corresponds to threshold frequency mu 0. Okay, so here when the curve intersects with x-axis, the kinetic energy will be equal to 0, and when the kinetic energy of the electron is 0, so energy of the photon will be equal to W0, so mu equal mu 0. So here the frequency in this case at this point is the threshold frequency where the kinetic energy of the electron is 0. We can deduce, as we increase the value of the frequency of the radiation, the kinetic energy of the emitted electron increases, because as the frequency increases, the energy of the photon will be increased too, and W0 is constant, so the kinetic energy increases. In application 4, we hit the sodium metal by different radiations of different frequencies, and for each frequency we record the value of the kinetic energy of the emitted electron, and we tabulate the results. Okay, now pause the video and solve this application. In part 7, we observe that the line of the second metal, the red line, is parallel to the blue one of sodium. Why is that? Because h is constant, and h is the slope in the Einstein's relation, so for any metal the straight line will be parallel to the sodium or any other metal. Now open your books and solve exercises 8, 9, 10 and 11, page 280, or simply you can pause the video and try to solve them. Quantum efficiency. Power of the radiation. The average power of an incident radiation is P equal energy total per unit of time, okay, equal nh mu per unit of time, where n is equal to the number of incident photon on the surface of the metal. The average power also can be written in the form P equal n times h nu, where n here is the number of incident photons per second. The quantum efficiency. First, let's talk about the effective and ineffective photons. Okay, among the photons that are capable of producing photoelectric effect, many of these photons fail to cause photoelectric emission due to different reasons. Okay, these photons are called ineffective photons. The rest of the photons that cause the photoelectric emission are called effective photons. Okay. The quantum efficiency is equal to the ratio of the number of effective photons to that of the total number of the received photons. So R, or efficiency, equal n of the effective photons over total number of received photons. Okay, we can write number of emitted electrons per over number of received photons. Note, the number of effective photons is equal to the number of extracted electrons, and the number of extracted electrons increase as the number of incident photons increase. Now try to solve exercises 12, 13, 14, 15, 16, page 280 using your official book. Finally, we will talk about duality theory of light. Light behaves as both particles and waves at the same time. In diffraction and interference, we use wave aspect of light to describe the phenomenon of diffraction and interference, while in photoelectric effect, we consider that the light is a particle. We use the particle theory of light. Diffraction and interference are evidence of wave aspect of light. Photoelectric effect and other phenomena are evidence of particle theory of light. The conclusion: light has a dual nature. Here we have 4 different sessions. Try also to pause the video and solve these sessions. Dear students, thanks for listening. See you in new videos.